This is Algebra 2 at Trig, Unit 6, actually 9.6. We're doing probability with dependent events. So two events, A and B, are dependent events if the occurrence of one affects the occurrence of another. So in the past, we have flipped a coin. Heads or tails, that is independent. It doesn't affect the next flip, whatever the previous flip was. Or if you put a card back into the deck, you always have 52 cards, though that would be independent. If you keep the card out, and now you only have 51 cards, that would be dependent. It changes the probability in the next draw, so that's what makes it dependent. The probability of B, given that A occurs, is called conditional probability of B given A. So that's the probability of B, and we draw a line straight down, given A. That is not a fraction. That's B given A. So this bar is the word given. B given A. So what that's going to look like, so when we're working with dependent events, so you got to know your storyline. You've got to look at to see if each event is affecting the previous one. So A and B, the probability of A, and in the past we've said times the probability of B, because they don't affect each other. But now it will affect it, so it's the probability of B given A. So that's how we write that, the notation. And if you want to manipulate this, you can still get the probability of B given A by itself. Here's B given A. By dividing away the probability of A underneath A and B. The probability of A and B divided by the probability of A. That would give us the probability of B given A. So just different ways to manipulate your equation. So we come down and we look at our table, and it shows the status of 200 registered college students. What's the probability that a randomly selected student is female? So we notice here that the female students are 120. The male students are 80. Together, that's making 200 students. So that's matching what they're talking about in terms of the number of students. So what's the probability that we have selected a female? Well, the favorable, in this case the females, over the possible, which are the total students, can be reduced to 3 over 5. So that's pretty straightforward. Now, if a female, so given it's a female, what's the probability of a full-time student? So the probability of a full-time student, given we're only looking at the females. So if you're just going to look at the female list, the full-time student would give us 40 out of the females, which is 120, and that can reduce to 1/3. So there, this is considered dependent. Here we'll see how dependent affects the different probabilities. You randomly select 2 cards from a standard deck. What's the probability that the first card is not a heart and the second card is a heart? The first time we do it, we're going to replace the card. The second time we do it, we won't replace the card. So if we replace it, this is considered independent. Because you're putting the card back in, it's not going to change the probabilities. So we want the probability of not a heart. Then we want the probability of a heart. So we're going to multiply those two together. So not a heart. How many cards are not hearts? That's 39 out of 52. And we times that to the 13 out of 52. That can be reduced to 3 out of 16, which is 0.187. This here is 1/4. Actually, 3/4, sorry. This is 3/4, this is 1/4. So we can get 3 over 16. Now, what if you don't replace it? What if you keep that card out? Then this becomes dependent. Again, we want the probability of not a heart times the probability of a heart given, and we draw that bar, first card is not a heart. Okay, so what's the probability of not a heart? 39 out of 52. And then what's the probability that we do have a heart given the first card was not a heart? And don't forget, we're not replacing it. So that's 13, because we haven't drawn a heart yet, so that means there's 13 cards that are still hearts. But there's only 51 cards in the deck. So that's what makes it dependent. This probability is a bit different. So we get 13 out of 68, which is a 0.191. So you can see the probability is a little bit easier. The 39 out of 52 is the same, but the 13 out of 52 is more difficult than the 13 out of 51. So flipping back here, we're looking at dependent events. That are going to be extended to 3 or more events. So your teacher passes around a box with 10 pencils, or 10 red pencils, 8 pink pencils, and 13 green pencils. That was 31 total pencils. If you and 2 people in your group are the first to randomly select a pencil, what's the probability that the 3 of you all select pink pencils? So let A be that you chose a pink pencil, B is going to be the second person picked a pink pencil, and C is that the third person picked a pink pencil. This would be considered dependent events. because we're not putting the pencils back in. There's going to be less pencils every time somebody else draws, so this is dependent. It changes the probability. So we're looking for A to happen, B to happen, and C to happen. So we're going to do the probability of A, and we're going to times that to the probability of B given A happens. And then we're going to times that to the probability of C given A happens and B happens. So the notation is a little different. Notation looks funny, but it should make sense. We're going to have A happen. So we want a pink pencil. There are 8 pencils that are pink out of 31 total. If that person picks a pink pencil, how many pink pencils are there available now? There are now 7 pink pencils available out of 31 or 30 total pencils. And then if both of those are going to happen, then there would only be 6 pink pencils left out of 29. That can be reduced to 56 over 44.95, which is a 0.012. Not very likely that you're going to pick 3 pencils, all the same color, all pink in this case, in a row. Questions about that? Do you see how we changed the denominator? That's a big hint that this is dependent. When the denominator changes. All right, this would also be considered dependent. Using observations made of drivers arriving at a particular high school, a study reports that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult is wearing it, and only 26% of the time when the adult is not wearing the seatbelt. We want to know what's the probability that the high school student in the study is going to wear a seatbelt. Well, the student's going to wear a seatbelt dependent on if the adult wears it. So we know that 66% happen at that percentage, and 26% happen at the complement of that. So let's talk about that. We're going to make a tree diagram. That's going to help us identify which students are wearing seatbelts, because they wear seatbelts under different situations, independent situations. So an adult wears a seatbelt 0.69. That means the complement of that is 31% or 0.31. So they wear a seatbelt or they don't wear a seatbelt. That's the only 2 options. Click it or you didn't. Now, if you wore a seatbelt, what was the probability that the student wore the seatbelt? 0.66. So that means a student did not wear the seatbelt what percent of the time? 3, 4. So 90 and 10 would give you 100%. Another way that we could find students that are wearing seatbelts is to look at parents that are not wearing a seatbelt. Students wore it 26% of the time. That means they did not wear it 74% of the time. That has to add up to 100. They are complements. You either wore it or you didn't wear it. So if we want to figure out what is the probability that a high school student in the study wears a seatbelt, here's a student wearing a seatbelt, we can go this direction. Or we could go this direction. So we're going to look at the probability that A happens, which is 0.69, and this C happens from that branch, which is 0.66. Those get multiplied together. Or if the parent didn't wear the seatbelt, a student may have worn a seatbelt 26% or 0.26. So when we do that calculation, we get 0.536. What do you think? Okay, then we come down to some card questions. I did find out recently that the AP Stats test does not use card questions. All right? Don't know what that means, but we have talked about what the cards mean. We've talked about the colors and the face cards and all the details about them. We don't know what the background of the other students taking the AP test is, so they won't go to there. They'll do questions like this. They'll do questions with marbles and so forth. But just to let you know, that was an interesting fact. Okay, find the probabilities of drawing a given card or the given cards from a standard deck of 52. We're going to do with replacement for question number 1 and without replacement for question number 2. When we have replacement, remember, that is independent. And when we don't replace it without replacement, that becomes dependent. So that's the difference. That's when we have each one of these. The calculations are a teeny bit different. In both of these situations, we want to know the probability of having a face card, then a 7, then an ace. So the probability of a face card, we know that there are 12 face cards. That's these over here, the king, the queen, and the jack. We've talked about how those are face cards. So there are 12 of them out of 52 cards possible. Then we want a 7. Well, there are 4 7s out of the 52. Remember, we replaced the face card back, so there's still 52. Now we replace the 7 back, and now we hope to draw an ace. And there are 4 aces out of the 52. That reduces to 3 out of 197. That's a pretty low probability that you're going to get a face card, a 7, and an ace. And then if we're going to do this without replacement, these are dependent, we're still going to have 12 out of 52 face cards. We're still going to have 4 number 7s. But if you don't replace it, you're only going to have 51 cards. You're still going to have 4 aces, but now you're going to have only 50 cards. because you're keeping those other cards out. You're not replacing those cards back in. That's 8 out of 5525, which is a probability which is slightly better, 0.0014, because 4 out of 51 is easier or is a better probability than 4 out of 52. 4 out of 50 is definitely better than 4 out of 52. So this is going to be slightly better than that, but not dramatically. All right, so let's pause the video. You go ahead and work on these questions, and then we'll finish it off. Okay, we want to get a heart, then a club, and then we're going to get another club. We're going to replace them. So there are 13 hearts out of the 52. Then a club, there are 13 clubs out of the 52. And if you replace it, there are still 13 clubs out of the 52. That's going to reduce to a 1 out of 64, which is 0.0156. If you don't replace it, you still have the same probability for the first card, because there's 52 cards in there. But if you do not replace it, there are still 13 clubs, but there's only 51 cards. Now you want another club, but you already chose a club. So that means there's only 12 clubs, but there's only 50 cards. So that is 13 out of 850, which is 0.0152. A little bit more difficult to have that situation.